Okay, in this Institute Help video, we're going to look at another modified Atwood's machine. So one of the objects is on an incline, object A, and B is just hanging. So it's a little closer to a regular Atwood's machine. This probably actually makes more sense of how you would use an Atwood's machine. You would have some block dropping and that would pull something up an incline. This incline does actually have friction, so they give us the coefficient of friction. We're going to try to find the acceleration and both with and without friction. So the first thing I'm going to do, been doing it a whole bunch, free body diagrams. Free body diagrams. So let's start with object A here. So one force we can apply is our tension force. So there's going to be a tension. I'll call this Ft. And then another one we know is the perpendicular component. So I'm not going to draw the weight. I'm just going to go straight to the perpendicular component. So this is F perpendicular. And then another force would actually be the normal force. So that would be acting in this direction. These two should equal each other again. So since this rope is acting parallel to the incline, there's nothing perpendicular to the incline, we don't have to worry about them. Then, since it's being pulled up the incline, friction is going to try to oppose that, and we also have a parallel component. So I have two forces acting downward. I have the parallel component, so F parallel, and I have friction, if it's there. So since I'm going to do this one with frictionless and then with friction, I'm going to go ahead and draw it in as if it's there, and then we can just make it 0 for part A. The other one I'm going to draw a free body diagram for is B. B is going to be really simple. It basically just has a tension force acting on it and its weight pulling down on it. So let's change the green a little bit just so you can kind of see. So this is going to be, I'll just write this as MB times G. So it's the weight of mass B. So I'm going to actually do this the way I do all Atwood's machines, is draw or write equations for the fact that these objects can accelerate. So if this is dropping, we're assuming that this block is going up the incline and this object is dropping. It doesn't have to be that way, but we have to pick a direction. So I'm just going to pick a direction. Also, even though it looks like mass A is huge compared to mass B, if you read the problem, mass A is only 12.3, but mass B is 56.7. It's so much heavier, so much more massive, so we kind of assume it. So I'll start with A, and I'm going to draw this with everything in it, and then I'll look at the frictionless situation. So it's going to be moving up or down the incline, so I'm going to write Ft as the first force, and it's acting up the incline. That's in the direction. And then the parallel component and friction are acting opposite that. So I am going to subtract my parallel component. I'm going to subtract the friction component. And the friction is going to end up being kinetic because we're actually going to be moving when we do part B, but I'll have that. And so this would just become 0 if I don't have it for part A. And this whole thing should equal mass A times this little acceleration. I'm going to go ahead and write that in this kind of maroon color. So that's my first equation. My second equation is going to be for mass B over here. And so when I do mass B, I notice that the weight is in the direction that I have actually written for this. So this is going to be mass B times gravity is in that direction. And then this time, the tension force is in the opposite direction. And that should equal, let's see, let's come up with a different color. Let's do purple. Mass B times the acceleration. Okay, so those are my two equations. Before I start substituting in, basically what I'm going to do with these two equations, I'm going to add them together. So my FTs are going to end up canceling each other. So they'll just kind of disappear, and I'll just be left with everything else. So I end up with mass B times gravity. This is just like I would have on a regular Atwood's machine. And then I'm going to be subtracting the parallel component. I'm going to go ahead and write in how I find that. So this is going to be mass A times gravity times the sine of the angle follow the incline. So they gave that 25 degrees to me. And then I would subtract the friction component. So the friction is going to actually be the fun equation. So it'll be the coefficient of friction times the normal force. But the normal force equals the perpendicular component. So when I write this, it's going to be mu k times ma times gravity times the cosine of theta. And that should equal the sum of these two things. So it's going to be mass A plus mass B, that quantity, times your acceleration. So since I have the masses, I know the coefficient, I know the angle, I know gravity, I know everything except for the A, I can find it. So this is our ultimate equation. Now in part A, I don't have any friction, so I can get rid of that part and it'll just disappear. In part B, I'll have everything. So it's just a matter of how much I want to do. And so the idea is I'm just going to be dividing by the total mass to actually find it. Hope this helps.